Now the properties. First, the physical property. Let us go for the important physical properties, that is boiling point and melting point. Now, let me give you two important things. See, boiling point is directly proportional to the number of carbon atoms. In fact, directly proportional to molecular weight. Right. Greater the molecular weight, greater is the boiling point. It is because as the molecular weight increases, van der Waals forces also increase. Okay. So this is point number one. Now if suppose the number of carbon atoms is same, I mean in case of alkanes with the same number of carbon atoms, in such a case, as the branching increases, boiling point decreases. But why? You know, as branching increases, surface area decreases. We'll give you an example. See, when surface area decreases, the molecules become more compact. Right. They become more compact and even more spherical also. As and when they become more compact, in order to separate them from the association or to overcome the van der Waals forces, you require more boiling point. Sorry. As and when it becomes more compact, as the surface area decreases, it becomes more compact and more spherical. They'll be away from each other. As a result, boiling point decreases. So as the branching increases, boiling point decreases because surface area decreases. Okay. Let me give you an example on this. The boiling point of neopentane will be less than that of. Let me give you the option. Isopentane, N-pentane, N-butane, and N-hexane. Okay, let us see. The question is, the boiling point of neopentane will be less than that of. So you have to check for those which have got more boiling point than neopentane. Am I right? Now, see, isopentane and N-pentane, even the neopentane, they have got 5 carbon atoms. N-butane has 4 carbon atoms. N-hexane, of course, will have 6 carbon atoms. Right. So at the first site, we can say that N-hexane will have the highest boiling point. Right. With 6 carbon atoms. Then how about those with 5 carbon atoms? Let me give you the structure. N-hexane is CH3, CH2, 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 CH2. Then coming to N-pentane, isopentane, and neopentane. So this is N-pentane. Then look at this. Isopentane. Iso is this. This kind of an arrangement is called iso. Then the neopentane, having quaternary carbon atom. This is neopentane. Now as we go from N-pentane to isopentane, isopentane to neopentane, there is decrease in surface area, or say there is increase in branching, right? So as the branching increases, we know that the boiling point is going to decrease. N-pentane, then isopentane, then neopentane. And finally, the one with just 4 carbon atoms, that comes here. N-butane, CH3, CH2, CH2, then CH. So the answer for this question is going to be, it will be less when compared to, of course, N-hexane, N-pentane, then isopentane. Hope this is clear. So first, go for the number of carbon atoms. Greater the number of carbon atoms, greater is the boiling. Then if they have the same number of carbon atoms, check out for the one which is more branched. More branched will have less boiling. That's it. Now going for the second interesting thing, that is melting point. This is a bit complex. There is something called alternation effect or oscillation effect. What do you mean by oscillation effect or alternation effect? Check this out. I have two important things. Melting point increases more on moving from an alkane having odd number of carbon atoms to even number of carbon atoms. I'll give you some values. Let us see then. But for now, see this. Increases more on moving from An alkane with odd number of carbon atoms to even number of carbon atoms. Odd to even increases more. Of course, vice versa. Melting point increases relatively less on moving from an alkane having even number of carbon atoms to odd number of carbon atoms. Of course, there is a increase, but increase is relatively less when you go from even to odd. Why is it this? The reason is very clear. Alkanes with even number of carbon atoms are more closely packed is the reason. Because they are more closely packed, they'll have more melting. Okay, so as usual, melting point is directly proportional to number of carbon atoms. But this is how we have to check. And see, because of this, we call it oscillation effect or alternation effect. Let me show you what oscillation effect is or what alternation effect is, taking the values which I remember. Let me give you an example. Now, suppose if you consider N-pentane, you know, for N-pentane, the melting point is minus 130 degrees centigrade. See, for isopentane, it is minus 160 degrees centigrade. So from N-pentane to isopentane, see, there is a decrease in the melting point. Because there is increase in branching. But then, see the melting point of neopentane. Minus 17 degrees centigrade. Now, this is a bit interesting. Minus 130 to minus 17. Branching has become more and more, but the thing is, there is a increase in melting point. So we cannot actually give a generalization with regard to branching in case of melting point. So this is in case of alkanes with 5 carbon atoms. Let me give you 2 more for clarity's sake. See, in case of N-hexane, the boiling point is, the melting point is minus 95 degrees centigrade. So from N-pentane to N-hexane, what has happened? From N-pentane to N-hexane, the number of carbon atoms is increased. Even the melting point is also increased. minus. Then go for N-heptane. See, in case of N-heptane, it is just minus 90.5 degrees centigrade. Look at what has happened. See, from minus 95, the melting point is increased. Of course, increased, but see the magnitude. From N-pentane to N-hexane, that means from odd to even, increase is more. From even to odd, from N-hexane to N-heptane, of course there is increase, but is less. This is what I said, alternation effect. So this is a quite interesting point. So we cannot give a generalization with regard to branching also. Of course, with regard to the number of carbon atoms, we can simply say that melting point is directly proportional to the number of carbon atoms. There is no doubt about this. Okay, so next. The chemical properties. See, alkanes undergo free radical substitution reaction. Right. What do you mean by a substitution reaction? Simple substitution of an atom by another atom or a group of atoms by another group of atoms. And what is free radical substitution? One free radical is substituted by another free radical. That's it. Okay, now let us straight away go for halogenation. Right. What is halogenation? The alkanes react with the halogen in the presence of sunlight or UV light or at high temperature 250 to 400 degrees centigrade. Simple. A hydrogen free radical is replaced by a halogen free radical. So we get Rx and HX. Mechanism is very interesting. Now it occurs in 3 steps. The first step is chain initiation. In this, the halogen molecule undergoes homolytic fission in the presence of sunlight or UV light or at high temperature. So when homolytic fission or homolytic cleavage occurs, we get free radical. Here we got halogen free radical. Okay. Now, the second step is chain propagation. See, in chain propagation, the halogen free radical formed in the first step reacts with the alkane molecule. So here you get these two. Now, simple, add these two. Just a minute. We should actually get alkyl free radical. R free radical is what we get because this is going to react with hydrogen halide. R free radical and HX. Then this R free radical will now combine with the halogen. Here you get this. Now in this step we get Rx. Rx plus the X free radical. Now this X free radical again goes into the first step. So simple is halogen free radical combines with an alkane, alkyl free radical combines with a halogen. So this is chain propagation. Then coming to chain termination. See, in chain termination, any two free radicals combine. Now remember, this chain termination step is always exothermic. Any two free radicals, say two halogen free radicals combine to form X2, or two alkyl free radicals combine to form alkane, or one alkyl free radical combines with one halogen free radical to form alkyl halide. Okay. Then let me give you some important points here. There are certain initiators which initiate the chain reaction. I have peroxides, see these peroxides in the presence of sunlight or at high temperature undergo homolytic fission and we get alkoxy free radicals. Now these initiate the reaction. Now there are per esters which initiate the reaction. Look at the per ester. Now even these, in the presence of sunlight or UV light, undergo homolytic fission to form these free radicals which initiate the chain reaction. Now these are the initiators. Of course, there are inhibitors which slow down or even stop the reaction. For example, oxygen. See, this oxygen interferes in this way, combines with the alkyl free radical to form this, to which another alkyl free radical gets added up to form a peroxide. See, because in this, the alkyl free radicals are consumed, are used up, so reaction is stopped or is inhibited or is slowed down. See, in this, the alkyl free radical is combining with the oxygen. You can show it this way. Oxygen, take it this way. You get oxygen, oxygen free radical. Now these two combine to form a bond. You are left with this free radical. Okay, so this is how there are inhibitors, there are initiators for chain reaction. Now let us go for the different types of halogenation reactions. Coming to the first one, that is fluorination. See, there are two types of fluorination. The first one is direct fluorination, in which methane reacts with fluorine, which is with maximum reactivity. Okay, it reacts vigorously. I mean with explosive speed, upon which you get carbon black. Reaction occurs with explosive speed. Then the second one is indirect fluorination. Now in this, fluorine, which is most reactive among the halogens, is diluted with nitrogen gas so that it becomes less reactive as compared to original. Now in this case, of course, the regular reaction occurs. This is how the reaction goes. Now even chlorination also. Even in chlorination, I have two varieties. First one is where chlorine is taken in excess. Chlorine is in excess. If you consider this, all the four hydrogens get replaced by halogens and you get carbon tetrachloride. Right. Let me show you the same stepwise. See, in the first step, methane reacts with chlorine in the presence of sunlight. a hydrogen free radical is replaced by chlorine free radical and you get methyl chloride. Right. Now this methyl chloride further reacts to form methylene chloride. Then this methylene chloride on further reaction with chlorine gives chloroform. And chloroform further reacts to form carbon tetrachloride. Right. Yes. So this is when you got chlorine in excess. Second thing is when you got methane in excess. Reaction stops in the first step itself. Methyl chloride, then HCl. I have different cases here. See, when the reaction is carried out at room temperature and under dark condition, you will have no reaction because no free radicals are formed in this case. Okay. Now coming to the second, at 300 degrees centigrade and in darkness. See, here you got high temperature, reaction occurs. Then using peroxide and at 100 degrees centigrade, even this also is okay because you are using the chain initiators, I mean peroxides, and you are also using some higher temperature of about 100 degrees centigrade. Even in this case also, reaction occurs. Right? Then it can also be carried out using tetraethyl lead. It is called TEL, anti-knocking compound. Knocking is explosion, anti-knocking, which prevents explosion. Even in this case also, reaction takes place. Okay. So this is all about reaction of methane with chlorine. The first one when chlorine is in excess. Second one is when methane is in excess.